Alright, today we're going to experiment on molar heat of combustion. That is, we're going to look at the change in enthalpy, meaning the amount of heat energy released from two different alcohols when we burn them. So the first alcohol we've got is isopropanol, which is also known as isopropyl alcohol, and then we've also got ethanol. So two identical containers. We haven't done any measurements yet. So you're going to need some pen and paper, because what I jot down, you should jot down, and then you need to solve some calculations. So we've got the aim to compare it. And what are we comparing? The delta HC, which is the molar heat of combustion, or the enthalpy of combustion. We know it's an exothermic reaction. We know we expect negative values. Some of you might ignore the sign, but the value we expect to be roughly 1300 kilojoules per mole for ethanol. And you're going to have to look at some reference data on the isopropyl alcohol. Your conclusions should not just compare which alcohol released the most amount of energy, but it should also look at the amount of heat loss. And we should hopefully have the same percentage error in both experiments. So your result table, you've got two of them, one for the measurements and then one for the calculations down below. Okay, so firstly, what are we going to measure? For two different alcohols, so we're going to burn both of them for 5 minutes, and we're going to heat up some water. Let's have a look at the apparatus. Looks like this. So it acts like a heat shield. So we're doing ethanol first. It'll go there. We'll take the lid off after we've done our measurements of the weight, and we'll pop on our, it's like a tripod. This one's got some holes to let the oxygen in so the burner stays alight. We'll have a container full of water. We'll take the initial reading for the temperature of that water, wait until the temperature is stable, record it as TI. We need to make sure we knew the mass of the burner before we lit it. Because what we're going to do at the end, after 5 minutes, we're going to pop the blue cap back on, reweigh that in order to find the final mass of the burner, and that final mass of the burner will give us the amount of alcohol burnt. So a bit of a windshield here. We're going to prevent as much heat loss as possible. As I said, we'll heat it for 5 minutes. A bit of stirring is a good idea to make sure the entire mass of water that we put in there absorbs that amount of energy. Okay, the energy from our chemicals. Some interesting points to make. The energy from these chemicals, right? Energy is not a particle. It doesn't take up space. If you weighed out the reactants for this reaction and you weighed out all the products, it would obey the law of conservation of matter. So all the atoms are still there and they still weigh the same. The energy came from something else. It came from the bonds. It came from the stored potential energy. And that is, it's called enthalpy. Okay? So energy doesn't take up space. It isn't something really physical in that regard. And in order to measure it, we're tracking temperature. Okay? The heat is a measure of how fast the particles move. And we know that it's going to release all that energy. So the water is going to increase in temperature. So here are the measurements just to make sure you're aware of them. I'll be tracking throughout this experiment over the next 5 minutes for ethanol. How much mass was in my burner to start with? The burner mass, the initial, I for initial, in grams. The burner mass, the mass of the burner, the spirit burner that is, in grams. And that's the final mass. At school, the burners look more like this, and I decided not to use this one and go with some stem burners that are used for a steam engine. Mainly because, well, enthalpy is all about the energy that you can use to do work, like run an engine, but I also want my burners to be the same, and I've only got one of those. So we're going to use two of those small burners. Once we figure out the initial mass and the final mass, you guys will be able to figure out the moles of alcohol that is burnt. So I suggest you put that information somewhere. Unfortunately, we ran out of space for that, but you'll need to find, before you can find the delta HC, you'll need to find the delta H and divide it by the moles, and then get those kilojoules divided by mole, per mole. All right, so some of the raw data that you'll need to get there though, I want us to get the most valid result possible. So we're going to take into account every bit of energy that we believe the reaction gave off. So we're going to look at how much the glass, conical flask weighs in grams in order to work out the exact amount of energy that goes into the glass. We're going to assume that it has the same initial temperature as the water, and we'll track how much water was inside the glass, the conical flask, and that will be in grams as well. Okay, so the initial temperature of the water will be considered the initial temperature of the glass, and so will the final. So some of the calculations you'll make from this data for both alcohols, the ethanol and the isopropanol, also known as isopropyl alcohol, you're going to compare them. They'll have different delta T's. If we run them both for 5 minutes, one's going to release more energy than the other, perhaps because it's got more bonds to be broken and more bonds to be rearranged. And that's because its molar mass is different and its formula. So the quantity of joules released into the glass, quantify that using the MCAT equation, mass of glass times capacity of glass to absorb energy times the delta T of the glass. Do the same separately for the water, the quantity of energy that goes into the surrounding water, because the glass is also part of that surrounding system. The surroundings, the system is the reaction. The quantity will also be a MCAT calculation, but it's going to be the mass of the water times by the change in temperature. But don't forget the C in MCAT, which is the capacity of water to store energy. So it takes 4,180 joules per each kilogram. So it's a bit of a conversion there. We're measuring in grams, but you need to be aware of the kilograms of water and how much temperature it changes by. So for every 1 degree Kelvin or 1 degree Celsius it goes up by, if it was a kilo of water, it would take that much energy. So you're going to add that as your C value in your Q calculation, but then sum your two Q values. If you're getting two different Q values, we're going to get a nice bigger value for Q, and therefore a bigger value for delta H, and a bigger value for delta HC, which will hopefully minimize the amount of heat loss that we don't account for. We're going to need to do some research and find some data on borosilicate lab glass and find out its capacity to store energy, which would be a much smaller value than water. Hence why it's not very good for this sort of experiment. Some people would use glass, but most people would actually try and use something that's really good at conducting the heat from the flame into the water, such as a copper can. And they'd also account for the heat capacity of that can. Okay, let's start then. You're going to need to have that result table, and you perhaps will add the moles of the fuel as an additional column, as I suggested. We're going to get our conical flask, because that's what we've got available. It's 250 mils. We need to work out this mass, so we're going to tar a scale. Now, what if we use a kitchen scale? Should we see a difference? So a kitchen scale, maybe it can weigh greater amounts, but it can only go to a precision or an accuracy of the nearest gram. So 114. But if we use something a bit more analytical, we're getting 114.82. So as much precision as possible. We're going to minimize all sources of error. So that's going to be the same for both. Empty conical is going to be the same conical in both experiments, controlling as many variables as we can, and that is in grams. Double check always on your scale, so you should always see a unit. Sometimes those units can be changed into things like ounces, so always make sure you're right. All right, so we're going to tar it, and we're going to pour in an amount of water that will try to be consistent for both experiments. Now, of course, we could use the measuring cylinder to measure the amount of water. Unfortunately, I felt it more accurate to measure the water by its mass. Well, fortunately, not unfortunate. So we'll go for a nice round value, maybe 100. And we got as close as possible. And we'll record those decimals. You're going to be converting that to kilograms because your capacity of water value, the specific heat value, is in kilogram and not grams as part of its unit. So 100.58, we'll do this ethanol first. So the water mass, changed to 0.59. Okay. Now we've got that measurement, we're ready to start getting the initial temperature. It's good that we did this first rather than measure the fuel, because thermometers measure the temperature of themselves. In order for it to measure the temperature of the water, it needs to get into equilibrium with the water, the same stable initial temperature. So wait until that stops changing. Currently says it's on about 18, and we'll make them see if it drops any further in order to stabilize. Okay, so here's the ethanol. We need to keep track of our initial measurement. First, tar the flask, because it was tarred to account for the glass, and this is not using the glass. You need to also take into account, initially we used the cap, so when we reweigh it at the end, we'll make sure to put the cap back on. The cap's there to help prevent any loss by evaporation, which would also affect the mass. So we're not going to deduct the mass of the container, the burner, and that's not necessary. You'll see why later, I hope. So 22.45, 22.45. That is our initial mass for the burner. Let's get started with this experiment. This time we're testing ethanol. This is test 1. Let's take the lid off. It just lifts off. Put our heat shield / tripod on top. Center it. And light it. Start our stopwatch. Our timer for 5 minutes. The initial reading was 19 for the temperature. A bit hard to see this on camera, so that's why I didn't show it. 19. It's already gone up by quite a few degrees. About 4 or 5 already. Approaching 25, it started at 19. And that's only after a minute. So if you think about it, there's 100 mils in that sample of water. And with 100 mils of water, it takes 4.18 joules to heat up each milliliter or each gram by 1 degree. So because there's 100 grams, that would be 418 joules to heat up this sample by just 1 degree. It is already heated up to about 50. So it started at about 20, that's already almost a 30-degree jump in temperature. And each of those degrees is going to be about 418 joules that was sent from the chemical system to the surrounding glass and water. Technically, the glass is also getting hotter. Just to make sure we're getting a reading that's not inflated and too high, we're going to do some stirring. We don't want a pocket of water at the bottom to do all the absorption of energy. We want the entire sample of water to be involved in this heat transfer. About a minute left. Final temperature. Which is 70. Let's also quickly stop at the flame, extinguish it. And before any of the fuel evaporates, let's weigh it again. So initially, this burner weighed 22.45 grams. It now weighs 20. Must be some fast evaporation. We'll take the higher reading of 20.12, and that means we've burnt over 2 grams of fuel. So the difference in those two values, TF minus TI, will give you the delta T.
Last time we tested ethanol, and now we are going to test isopropanol.
You heard that, folks? Ethanol was our last experiment. Now we're up to isopropyl alcohol, commonly used for nail polish remover or sanitizing your hands, so is that. And we're going to call it isopropanol to be a bit more technical with our RU-Pack chemical names. Alright folks, 26.85 grams of ethanol. We're going to take our lid off. We're going to get our heat shield / tripod. Into that, get our conical flask ready and light it up. Go. Okay folks, remember, stirring is important for these experiments. Otherwise our mass of water is lying to us, and the mass of water is not that little bit of water touching the glass, it should be the entire amount of water. So the flame, it is lit, it looks very clean and blue, but it is a light. And we're going to now time it for 5 minutes and then take our readings. In order to minimize the effect of heat loss to the environment, or heat loss by accidentally boiling some water that was stuck to the bottom of the flask, these sources of error, we can minimize them by repeating and trialing this experiment over and over again, averaging our delta HC value each time, ignoring any of the outliers. Now these sort of experiments, it is important to note that the color of the flame tells you how cleanly the fuel is burning. And if the flame was super yellow, then that's a signal of incomplete combustion, and that's also going to give us a source of error. We are assuming that the reaction type is complete combustion, and that's usually a blue clean flame where no carbon soot residue stays behind. If you are getting a yellow flame, it does signify an alternate, different reaction is the one that's proceeding, and therefore you're not actually getting the delta HC for the reaction you expected. You're getting the delta HC for a different reaction. So we need to make sure that as best we can, we keep that flame blue, clean, completely burning, with very little soot residue of unburnt fuel. And generally when you test the bigger alcohols, because there's more carbons, it requires a higher stoichiometric amount of oxygen, the ratio of fuel. Doing these sort of experiments indoors is not recommended unless you have adequate ventilation. The fumes from these bigger alcohols, because it is incomplete combustion, can be a bit toxic, as it is releasing carbon monoxide and soot and unburnt fuel as byproducts, perhaps slightly decomposed fuel. Alright, that's pretty much 5 minutes, showing that the flame was still on the whole time. So we weighed it with the lid before, weighed it with the lid after, 24.57. So you'll notice it did get hotter. You'll notice it burnt roughly still 2 grams of fuel, so about the same amount. The burnt rate is about the same as you expect, same size opening, same amount of airflow available. So it's burning the fuel about the same speed. Although this one might be a little bit different due to stoichiometry being slightly different. However, we got a lot hotter this time around. You can use your logic and think, well, that means because we had the same amount of water being heated up and the same amount of glass being heated up, we gave it more heat, we gave it more energy. So our Q values should be lower for ethanol, higher for isopropanol. What's going to determine the delta HC though is whether or not the moles was bigger or smaller. Alright folks, you got your pen, got your calculator, give you some extra information to help you there. For ethanol, formula C2H6O should give you a molar mass for calculations of 46.068 grams per mole. Isopropyl alcohol or isopropanol, formula C3H8O, so it should give you a molar mass of 60.094 grams in every mole. Now that means that you should pause this video, do your calculations, and then hit unpause and compare your answers. Alright, you've unpaused the video, you're ready to compare your answers. So for moles of ethanol, you should have gotten 0.05. And we're not going to round the value until the very end, so I'm putting a more precise answer there. Moles of isopropyl alcohol, a little bit less. And that's to be expected. Even if you're burning 2 grams of each one, you're burning less moles or molecules because each of those molecules of this bigger alcohol, way more. So we got 61 for the delta T of isopropanol, 52 for the delta T of ethanol. We're using those values here in our Q calculations, the surroundings, how much energy do they absorb? So they went up by 52 degrees for ethanol, they went up by 61 degrees for isopropyl alcohol. You have to take into account that each of these materials have different heat capacities. So if you did correctly research it, well, the one I found was 800 joules for every kilo of glass, and it was 0.114 kilos of glass. So multiply all those values as per the datasheet equation, and you're getting 4,776 joules went into the glass. Do the same thing for the ethanol, still the same amount of glass, the same flask was used, still the same capacity, it's a specific heat, and it's a constant 861, so it's a slightly bigger amount of energy went into the glass because the glass got hotter when you tested the bigger alcohol. Now the smaller alcohol, we used about 100 mils of water, so 0.1 kilos, 4,180 joules went into each kilo in order to heat it up by 1 degree, but it went up by 52 degrees. So MCAT, that calculation gives you 21,864 joules, or 21.86 kilojoules. So converting those to kilojoules, we should be getting 26.64 for our total Q that went into the surroundings, quantity of energy that went into the surroundings using the small alcohol. 31 kilojoules went into the surroundings for the bigger alcohol. The molar enthalpies. Converting the quantity of energy that goes into the surroundings to the quantity of energy that the chemicals gave off, their potential stored chemical energy. Well, this is a opposite trend. So you've got to change the sign in order to show that it is the opposite. The amount of energy that went into the water in the glass is an energy amount that was lost by the chemicals. So that's a deduction, it's a minus. So minus 26.64 kilojoules, and that is for the small alcohol, ethanol, minus 31.073 kilojoules for the bigger one, the bigger isopropanol. Dividing that by the moles that we calculated previously to get the amount of kilojoules we would have been getting for every mole that we were using. And had we used 46 grams of ethanol, we would have expected to have been able to obtain that much energy into our surroundings, 526 kilojoules. But if we are representing it as not just a raw heat of reaction value, we need to put a minus there to show it is a change in enthalpy value. Change in enthalpy for the bigger alcohol is bigger, minus 819 kilojoules for every mole that we were burning. So let's do some comparisons. If you do some research on Google, chemical data, theoretical reference data for ethanol is a lot higher. And if you are calling it a heat of reaction, you don't need the minus sign. But if you are calling it an enthalpy change, a molar enthalpy change, we could show it as a minus 1360 or 1,360 kilojoules should be released for every mole of ethanol that you burn. Whereas minus 2,006 kilojoules, that's how much energy the ethanol is lost, or sorry, the isopropanol. So really it's not, this is, if you ignore the minus, then you're saying, oh, that's how much energy it is releasing. It's releasing 1360, it's releasing 2006. Or ethanol releases a little bit less than isopropanol. But isopropanol, if you're going to now call it an enthalpy value, a change in enthalpy, a delta is a change, then you're writing the minus sign in front of it. It is per mole, so that we can now compare to our per mole values. So our final step to compare. We're going to find it nice to do a percentage of error or heat loss. So we find the difference in the values. That's the amount of heat that we did not quantify and measure. That's our loss. And we get slightly more heat was lost by the isopropanol because it was releasing more heat to begin with, divided by the total amount of energy that we should have been able to capture had we burnt 1 mole. So we ignore those signs in front, the negatives, because it wouldn't fit this context. We're just looking at the errors in the value. We get, what's nice is a percentage that is roughly the same. So you're getting roughly 60% heat is lost, showing that this apparatus that we've set up allows you to capture 40% of the energy that the reaction gives off. So it's 40% efficient. Not too bad, but not that great either. Thanks for watching.